We're now going to look a little bit deeper into isomorphisms, studying something called invariants in isomorphic rings. First, we're going to define what an invariant is. We're going to define it in two ways, both informally and formally. We're going to look at some properties and show how to prove a particular property is an invariant. We're going to look at how to use an invariant to prove two rings are not isomorphic. And then we're going to list some invariants. Alright, so first I want you to remember what addition and multiplication tables look like and what kind of information we can glean from them. So here's a ring that you've actually seen before, and here's the addition table and the multiplication table for it. So the question I want to ask is, what information can we infer just from the tables? Well, the first thing is, if we look at the first row and the first column of the addition table, we can tell by that A is an additive identity because it leaves everybody alone when we add it to different elements. Looking at instances where A appears in the interior of the addition table, we can use that actually to show what additive inverses are. And everywhere there's an A, there's two elements that are being added together to give you A. Those are additive inverses, and we can see that every element is its own additive inverse. If we look over in the multiplication table at the last row and the last column, we can see that the element D is a multiplicative identity because under multiplication it leaves all the elements alone. And if we look at instances where D appears in the interior of the multiplication table, that's where we look for units. And you can see that there are no units in the ring except for D. The only place that D appears in the interior of the multiplication table is where we have D plus D equals D. And finally, if you look closely at the multiplication table, you can use that to show that the multiplication is commutative. So what we've been actually doing in that example back there is looking at different properties that are invariants. In general, an invariant is a property that you can infer from the addition and multiplication tables. More formally, an invariant is a property of rings such that, well, I'm going to say that in two different ways. The first way I'm going to say it is when two rings are isomorphic, either both rings have the property or neither ring has the property. Or a way that makes it a little bit easier to prove something is an invariant. If R and S are rings such that R and S are isomorphic, and if R has the property, then S also has the property. So let's look at a particular invariant. It's going to be having a multiplicative identity. So our theorem is having a multiplicative identity is an invariant. So the definition of the invariant says that if you have two rings R and S with R isomorphic to S, we get to assume that R has the property. In other words, R has a multiplicative identity. And then we're going to show that S has a multiplicative identity. So we know that R is isomorphic to S. That means there's an isomorphism phi from R to S. And since we're assuming that R has a multiplicative identity, we're going to let one R be the multiplicative identity in R. Now, one of the things that we may be asking is, okay, we want to show that S has a multiplicative identity. What do you think? What do we think that multiplicative identity is going to be? Well, remember, phi tells us what role the phi of an element in R will take us to an element in S that plays that same role. So if we want something in S that plays the role of multiplicative identity, it makes sense that we look at phi of 1R. Now, how do we prove that's the multiplicative identity? Well, we have to look at every element in S, every little s in S, and show that phi of 1 times S is equal to S, and that S times phi of 1 is also equal to S. Now, one of the things that's going to help us is the fact that phi is an onto function, since it's an isomorphism. And that means if we have an element little s in S, there's some element R in R, such that phi of R equals S. So when we try to do things like compute phi of 1 times S, we can replace that S with phi of R, and then use the property of phi being an isomorphism to get phi of 1 times phi of R equals phi of 1 times R. Now we can use the property that 1 times R is equal to R, and we get phi of R. And remember, phi of R was equal to S, so that gives us S. So if we look at the beginning of that sequence of equations, we get phi of 1 times S, and at the end we get that that's equal to S, which is what we wanted to prove. Of course, we have to prove it the other way, but it's going to be the same thing. S is equal to phi of R, so we replace that. We use the properties of isomorphisms to show that phi of R times phi of 1 is equal to phi of R times 1. R times 1 equals R by the definition of multiplicative identity, and phi of R equals S by what we had before. So once again, we have S times phi of 1 equals S, and that means that phi of 1 is a multiplicative identity in S, which means that S has a multiplicative identity, and that means that having a multiplicative identity is an invariant. One of the nice things about invariance is it shows us how to prove two rings are not isomorphic. Remember, to prove two rings are isomorphic, we have to find an isomorphism between them. Invariants give us a way of proving that when two rings are not isomorphic. So for instance, if I wanted to prove that the integers are not isomorphic to the even numbers, I can perhaps find an invariant that is true in one of the rings but not true in the other ring. So we're going to prove this by contradiction. We're going to assume that the integers and the even numbers are isomorphic and prove a contradiction. And what invariant does one of the rings have that the other ones doesn't? Well, having a multiplicative identity. So we know that Z has a multiplicative identity, just the number 1. By the theorem we just proved, having a multiplicative identity is an invariant. Since we are assuming that Z and E are isomorphic, that means E has to have a multiplicative identity as well. Remember, an invariant means that either both rings have the property or none of them do. Since we know that Z has a multiplicative identity, that means E must have a multiplicative identity as well. However, we know that E does not have a multiplicative identity. It only has the even numbers. It doesn't have 1, and that is a contradiction. And that means that the integers are not isomorphic to the even numbers. So here are some other invariants, and I encourage you to try to prove that they are invariants using the definition. The number of zero divisors is an invariant. The commutative property of multiplication is also an invariant. Being an integral domain is also an invariant. Being a field. The number of elements is a ring is an invariant. Isomorphic rings should have the same number of elements. And the number of units in the ring is also an invariant. The number of units in isomorphic rings should be the same. And finally, the characteristic of the ring is an invariant as well. So I'm going to give you some experience looking at invariants. The name of the PDF that has the in-class activities is called Isomorphic Invariants.